Hello, I'm Seema and welcome to part 2 of the chapter Hydrocarbons. In part 1, I introduced hydrocarbons to you and then I told you how do we broadly classify hydrocarbons. And then I also told you that each category of hydrocarbons is represented by a general formula. Now, before we proceed to the study of organic chemistry and hydrocarbons and other compounds in general, I would like to explain the general formulae a little more to you. We know hydrocarbons are compounds of carbon and hydrogen. And the simplest hydrocarbon, if we talk of saturated and unsaturated hydrocarbons, the saturated hydrocarbons, the simplest hydrocarbon consists of at least one carbon. Since they are hydrocarbons, it is the number of carbon atoms which decides the prefix of the name or the word root of the name. Now, for example, C, if it has only one carbon, carbon has a valency of 4. It has 4 electrons in its outermost shell, which is the second shell, and it needs 4 electrons to complete its octet. Therefore, every carbon in any hydrocarbon should form 4 bonds. Right? Every carbon in these compounds forms 4 bonds. And it is this distribution of bonds, you've studied when we introduce organic chemistry, we tell you that carbon shows the property of catenation, that it can form chains with other carbon atoms, and it can show a variety of bonding because it has a valency of 4. So the simplest hydrocarbon would be where carbon is forming 4 bonds with 4 different hydrogen atoms. Carbon with 1 hydrogen, 2 hydrogen, 3 hydrogen and 4 hydrogen. So this is known as the first hydrocarbon, which is methane. Let us say that the hydrocarbon has 2 carbons, the simplest ones. So there are 2 carbon atoms, both of them connected by a bond. Now, carbon forms 4 bonds, so one it is forming with the other carbon, so it will form the other 3 bonds with 3 hydrogens. Similarly, this carbon is forming 1 bond here, so 2, 3 and 4. So every carbon should form 4 bonds, so this is forming 4 bonds with 4 separate atoms. The third member is CCC. Okay, there are 3 carbon atoms. Now, this carbon is forming 1 bond, so it needs 3 more hydrogens to complete 4 bonds. This carbon is forming 4 bonds, so it needs only 2 bonds to complete its octet or to complete 4 bonds. It needs only 2 more. This is forming 1 bond, so it needs 3 more. So 1, 1 and 1. So what do you understand from this? That every carbon is forming 4 bonds. And all of these are alkanes, because what is the definition of alkanes? They are saturated hydrocarbons, which means every atom is forming single bonds. So no more atoms can be added to it. Now, if we look at each member as we keep going down to the next member, let us say it has butane now, has 4 carbon atoms, 1, 2, 3 and 4. Instead of writing this detailed, this carbon is forming 1 bond. So how many hydrogens should it have? 3, right? So I can write H3. This carbon is forming 2 bonds. So how many hydrogens does it need? It needs 2. So I write CH2. This carbon is also forming 2 bonds. So how many hydrogens does it need? 2. And this carbon is forming only 1 bond. So how many hydrogens does it need to complete 4 bonds? 3 hydrogens. So I'll write CH3. Right? So in a way, logically, when you keep expanding the structures, you can write down the structural formula of every compound. But is there a pattern that comes out in these? Let us look at the pattern. This carbon, if we write the exact formula, number of carbons, number of hydrogens. This has 1 carbon, so we write C. And it has 4 hydrogens, so the formula of methane is CH4. What is the formula of ethane? It is C2H6. What is the formula of propane? It is C3H8. What is the formula of butane? It is C4H10. So we find that as we go to the next member, 1 carbon is increasing. Carbon went from 1, 2, 3, 4 and hydrogen went from 4, 6, 8, 10. So what do you see? There's a difference of CH2 between 2 members. The next member has 1 carbon more and 2 hydrogens more than the previous member. That is how homologous series are created. This is also something that you already know about homologous series. Now, how do we deduce the general formula? When you look at the number of hydrogens and the number of carbons in each of these, you can derive a relationship. What is the relationship? Let us say that the number of carbon atoms is n, okay? Whatever is the number of carbon atoms in each compound is n. Then what is the relation of hydrogen to this number n, to the number of carbon atoms? The first member we can ignore because deriving the relation here, we can come back to it to derive that relationship. But here, look, this is C2. 2 2s are 4 and 4 plus 2 is 6. We notice that if we double the number of carbon atoms and add 2 to it, you will get the formula of the alkane. So if there was 2 carbons, see the value of n is 2, the value of n is equal to 2. So 6, what is 6? 6 is twice n plus 2. Look, if this was 2, n is 2, then 2 into 2 plus 2 would be equal to 6. That is why C2H6 is the formula of ethane. Now in propane, the value of n is equal to 3. So if C is 3, 2n plus 1, how much would it be? Plus 2, how much would it be? It will be 3 2s are 6, 6 plus 2 is 8. And that is what we see, hydrogens are 8. There are 4 carbons, so n is equal to 4. So what will be the number of hydrogens? 2n plus 2 would be equal to 2 into 4 plus 2, which is equal to 8 plus 2, which is 10. So looking at this, what is the general, if whatever is the number of carbon atoms, we can say hydrogen is twice n plus 2, 2n plus 2. All alkanes can be represented by this formula. Let us say there is an alkane which has 50 carbon atoms. So value of n is equal to 50, C50. Then what will be the number of hydrogens in this alkane? You can easily calculate. It will be 2n plus 2 will be equal to 2 into 50 plus 2, which is equal to 100 plus 2 is 102. So you'll have 102 hydrogens in this alkane. That is why general formulae are important, and because they give away the formula of any compound in that series. So that was why a general formula is so important and why we learn it in organic chemistry. Let us understand the other general formulae now. Okay, so this was alkane, and let us take propane. Okay, and now I will not be writing the separate hydrogens. I'll just be writing the H3, H2 to make my writing simpler. Okay, now you have propane. Propane is CH3, CH2, CH3. Let us join the first carbon to the third carbon. And let us draw only the carbon skeleton. So you have carbon, carbon, carbon. And we are joining the first carbon to the third carbon. Every carbon is forming 2 bonds with the 2 other carbons. But every carbon forms 4 bonds. So it needs 2 hydrogens. So every carbon should have 2 hydrogens. Right? And it is a saturated hydrocarbon because all the bonds are single bonds. Every bond, it is forming 4 separate bonds, 2 with 2 carbons and 2 with 2 hydrogens. Every carbon is forming single bonds, and hydrogen as it is forms single bonds, so we don't bother about that. Now this is cyclopropane, right? It is a cyclic alkane. It is a cyclic saturated hydrocarbon. So what would the general formula of this be? We know that the general formula of alkanes was CnH2n plus 2. Let us see here, what is the formula? If I write just the number of carbons and hydrogens, it is C3H6. So what do I see? 6 is twice of 3. So we'll say CnH2n is the general formula. And why is it so? Why the additional 2 hydrogens are not there? Because the role of every hydrogen is to satisfy one valency of carbon. Every hydrogen is satisfying one valency of carbon. But if both the carbons are joined with each other, that is the place where the 2 hydrogens should have been, on the first carbon and the third carbon. to satisfy the last valency. But if you remove that, if you join these two carbons themselves, then there is no need for either of the carbons to be joined to hydrogens. So those two hydrogens will be reduced. This will become one hydrogen from this carbon, and one hydrogen from this carbon will be removed in order to form the cyclic structure. So therefore, you can represent all cycloalkanes by the general formula CnH2n. Let us come to alkenes now. For alkenes, the first member, what is an alkene? An alkene is a hydrocarbon which has at least one double bond between two carbon atoms. So the first member should have at least two carbon atoms, and there should be a double bond between the two carbon atoms. So let us complete this structure now. Whatever is the number of the skeletal carbon skeleton, the rest has to be filled up with hydrogens. So carbon is already forming two bonds. It needs two more bonds. So it will be CH2 and CH2. Right? Let us write down the structure of propene now. There are three carbon atoms, 1, 2 and 3. But there's a double bond between two carbon atoms. So this is propene. So what will be the formula of propene? This is forming two bonds, so this should have two hydrogens. This is forming three bonds. This carbon is forming three bonds. So how many hydrogens does it need? Only one. And this is forming only one bond. Therefore, how many hydrogens does it need? Three. So what? Write down the formula here. This is C2H4. And this is C3 and H is 6. Next member, fourth member, carbon, 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 4. Okay, and let us say the double bond is here. So this will be CH3. Wherever you have a single bond, there will be three hydrogens. Wherever you have three bonds already there, only one hydrogen. You have three bonds already here, so only one hydrogen. Sorry, it should be behind carbon. That's the way we write it. And here, since it is carbon chain, so here we write the CH3, H3 here. So this is butene. And butene, I'm not going to the exact name giving the locant, it's just butene. So what is the general formula here? What is the formula here? This is C4, and how many hydrogens are here? 3 plus 3, 6, 7, 8. So C4H8. Can you derive a relationship between number of carbons and hydrogens here? Whatever is the number of carbons is N, then hydrogen is double of that. Look at that. CnH2n. CnH2n. That is why the general formula of alkenes also, just like cycloalkanes, is CnH2n. Right? Isn't this interesting? And why, in the case of alkenes, why does the general formula of alkenes have two hydrogens less than alkanes? Again, the reason is simple. In the case of cyclic alkane, what was happening? The first and third carbon were forming a bond. But in alkenes, the same thing is happening. Instead of the first and last carbon making a bond, there is one additional bond between any two carbon atoms. Every additional bond that is formed will cause the loss of two electrons. So now come to alkyne, right? So you have the first member, C triple bond C, right? Now this is an alkyne. It has a triple bond between two carbon atoms. So three bonds, hydrogen is already formed, carbon is already forming, fourth bond with one hydrogen, fourth bond with one hydrogen, right? What is the formula? C2H2. Right? We can't derive a relationship here yet. So let's come to the third member. 1, 2, 3. And there's a triple bond here. This carbon is already forming 4 bonds. This carbon is forming 3 bonds. So it needs only one hydrogen here. And this carbon needs 3 hydrogens because it is forming only one bond. So how many carbons? There are 3 carbons. And how many hydrogens? 3 plus 1? 4. Hydrogens are 4. So what do we derive the relationship here? Cn 3, 2n was 6, and minus 2. Cn H2n minus 2. This has even 2 more hydrogens less than an alkene. Why will it have 2 hydrogens less than an alkene? It is simple. It will have 2 hydrogens less than an alkene because it has one more bond between 2 carbon atoms. And with every bond that is a multiple bond that comes in, 2 hydrogens, those 2 carbons which are joining together, they will lose 2 hydrogens. And that is why the general formula will change. Right? Isn't this interesting? Now, if we want to this was the basic hydrocarbons, and then comes benzene C6H6 because of its structure and the bonding. It has that formula. And then we don't go into the general formulae there because the benzene ring, whether it is benzenoid, aromatic hydrocarbon or non-benzenoid, and then how it is, it's more complex there. But for the open chain structures and the cyclic structures, the general formulae are really important here. Let us now go ahead from this chapter, that is hydrocarbons, and go to other hydrocarbons which may have a functional group. For example, if you have alcohols, whenever a functional group is added, just like what happened here, a bond was added in every new category. From alkane was the basic hydrocarbon, then we added a bond in alkene, we made a new bond in the case of cyclic compound, and we made an additional bond in alkene and then another additional bond in alkyne. If you want to add a functional group is also going to take the place of hydrogens in the hydrocarbon. A functional group also takes the place of hydrogen. It means that the bond that the carbon will form with the functional group will also result in the loss of hydrogen. So before a hydrocarbon joins the functional group, it forms an alkyl group. It is not actually the process of formation that takes place, but in the formula, it should have an alkyl group, and the alkyl group combines with the functional group. As I told you, that joining should take place with the loss of a hydrogen. So an alkyl group is that active group where an alkane loses one hydrogen. If it loses one hydrogen, it is that carbon to which the functional group will come and attach itself and form the compound. For example, let us take this propane. And in propane, alcohols have to be formed. So one of the hydrogens will be lost. The alkyl group will be formed. So if whatever, let us say this hydrogen is lost. So we'll have CH3, CH2, CH2. And this carbon is now active. It needs to form a bond. This, although we should not make a dot here because that does not mean that it is, it just has a free end. The dot represents a free radical, so I don't want to do that. So here, or it is a point where joining can take place, a free electron. It can be represented by a dot. So now the carbon here is active and it needs to form. It would combine with, let us say, if it was alcoholic group, it would combine with oxygen of the alcoholic group, and OH would join here and it would result in the formation of an alcohol. But before the alcoholic group added to it, now this group is known as the alkyl group. This is known as the propyl group. And what is the general formula of the propyl group? It has one hydrogen less than the alkane. So the general formula of any alkyl group will be CnH2n plus 1. One hydrogen less. And then if OH adds to it, it forms an alcohol. So what would the general formula of alcohols be then? It will be CnH2n plus 1 OH, because OH came and added to it. Every oxygen forms two bonds. It forms one bond with carbon and one bond with hydrogen. So this hydrogen, which belongs to the functional group, is not written in the general formula here. Because OH, when we write down the formula, we should be clear it is an alcohol. If we just keep the oxygen separate, we would not be able to understand which functional group is it, because oxygen is present in other functional groups also. So we need to know which functional group it is. So the atoms, the hydrogens that are present in the functional group will remain in the functional group. In the formula, they'll remain with that. So you write CnH2n plus 1 OH. So let us write the formula. What would be the formula of this is propanol. What will be the formula of butanol? It will be CH3, CH2, 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 OH. The butanol OL, that is OH, could add itself to other carbons also. If that would happen, let us say this carbon, it had to add to this carbon, then this carbon will lose one hydrogen and the OH will come and add here. But the general formula will still remain the same, CnH2n plus 1 OH. So that was how we write the general formulae of alcohols. For alkyl halides, if instead of OH you have a halogen, chlorine, bromine, iodine adding here, then what will be the general formula of an alkyl halide? It is the alkyl group and the halogen. So the general formula will be CnH2n plus 1 X, where X stands for a halogen atom. In the case of carboxylic acids, carboxylic acid, the functional group also contains a carbon atom. So the first member of a carboxylic acid, this is the first carbon of the compound. You've done this when you named the hydrocarbons. So since this is the first carbon of the compound, what will be the general formula for carboxylic acid? The general formula for carboxylic acid would be, the first member is COOH, should be there. Let me just make the detailed structure. I told you oxygen forms two bonds. Carbon, it forms a double bond with one oxygen, a single bond with one oxygen, and this oxygen forms another, the second bond with hydrogen. So that is the COOH. For the first member, this will have only hydrogen. HCOOH is the first carboxylic acid. The second member, the second should have two carbon atoms. Therefore, this is the first carbon atom. So second member will become CH3COOH. Third member will become CH3CH2COOH. So what would the general formula be? The general formula, again, what do you see? This is, if you look at this, CH3 is methyl group, right? This is ethyl group. But since the functional group already has this carbon, when we are writing the general formula of a carboxylic acid, we write the C here. But this is always the first carbon of the hydrocarbon, right? So the hydrocarbon actually, if let us say this is this has ethyl group, so we will not call this ethanoic acid. We'll call it propanoic acid because this carbon is actually a part of the chain. Although it has the functional group attached and carbon is a part of that functional group, yet it is the first carbon. So this will be propanoic acid. It has 3 carbons. But the general formula for a carboxylic acid is CnH2n plus 1, just like the alkyl group here, and COOH, where this C also has to be counted in the carboxylic acid. Similarly, in the case of aldehydes, it's the same. An aldehyde does not have the carbon with a double bond. It straight away has this bond with CHO. So, but the bonding is different. So, let us say you have an aldehyde. So, you have H, C, O and H. CHO group is like this, where carbon forms a double bond with oxygen and a single bond with hydrogen. Every carbon forms 4 bonds. This carbon is forming 4 bonds, 2 with hydrogen, 2 with oxygen, 1 with hydrogen here and 1 with the hydrogen here. So if you add a methyl group here, you'll get CH3CHO. We usually don't call it COH, we call it CHO. It's just, habit. Once you start, you won't be wrong if you call it, if you say OH, it might sound like alcohol. So whenever we are naming aldehydes or we are talking, we usually say CHO. And even when you're writing, you'll write CHO if you're not showing the bonds, because OH would mean alcohol. And even in carboxylic acid, the OH is there, but it is COOH. Therefore, it is carboxylic acid. So now what would the general formula of an aldehyde be? It will be CnH2n plus 1, CHO. Right? Where this carbon is also counted in the chain, and therefore the naming would be done accordingly, which you have already done in the naming of hydrocarbons in the previous chapter. So this is what I really wanted to explain once before I proceeded with the chapter. And with this, I'll wind up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.